So in this problem, you were given an infinite sum. So the example in the beginning was 1 minus 1 plus 1 minus 1 and so on. And you're given, in this problem, you will be given some kind of infinite sum like this that's periodic. And then the problem defines what is called the Cesaro limit of this sequence. And what you do is this. You compute every possible prefix sum. So let's start with what I will call S1, which is just the first number. And then S2, which is 1 minus 1. So that's 0. And then S3. So the problem defines these. So let's see. So this is 1 minus 1 plus 1. So that's 1. Right? And then the question is, what is the average values of these S when you take infinitely many of them? So mathematically, I would write it as the question is, what is the limit when k goes to infinity of the sum over s si I equal 1 up to k, and then we divide by k. So this is what the problem asks you to compute. And the realization now is this, okay? So if you look at these S's here, you can see that there's some kind of pattern here, right? Like S4, it would be 1 minus 1 plus 1 minus 1, that's 0. So as you can see, there's a periodicity even here in the S's. So it turns out that as long as the infinite thing you're given, I can give you another one here. It's 1 plus 1, 0. So we just repeat this. 1. Turns out that if you were to write down these prefix sums, then they will become periodic, right? So like, let me write down here, right? It's 1, then it's 1, then it's 0, and then the prefix sum, the next one is 1, 1, 0, 1, 1, 0. So these are periodic if and only if the sum of a period is 0. Okay? So, but let's say that these prefix sums are periodic. In that case, the answer is simply take the average of one period. So basically, if some of the data you get in is 0, then just return the sum of these S's divided by the period length. Otherwise, right, the sum is going to be positive or negative. And in that case, instead of it being periodic, it will just grow and grow and grow forever. Or if the sum is negative, it will just decrease and decrease forever. So in other cases, so if the sum is greater than 0, then what you should do is you should just print infinity. And for some reason, a lot of people did forget these two in the beginning of the contest. So there were a lot of errors because of that. Yeah, if sum is greater than 0, and then else, the last case. Yeah, elif. And then the last case is minus infinity. Okay. So I hope that at least, even if you struggle with this, and some people were, I hope at least you take away, this is something I find a little bit interesting, right? This kind of argument that, yeah, so I hope you at least learned something today from this problem, even if you struggle up there. And also, I don't think that the approach that tries to do this manually, I don't think that approach worked very well. And to my knowledge, there was no one that was able to estimate the average by manually summing things. But maybe it's possible. Or did someone do it? Did you get accepted?
Yeah.
Okay.
Yeah.
Okay, maybe. And okay. But this was the intended thing to note that these S's are periodic themselves, and that means that the average of all of them are like the average of one period. If the sum is 0. Yes. Okay. Yes. The phase paradox.
Yes. The next problem is phase paradox, which is Nils' problem. So I'm just going to switch back. Okay.
Next problem is phase paradox. In this problem, you're given two numbers n and m, and you need to find a list of numbers such that the average of the whole list is smaller than the smallest average of any subarray of length m. And this seems a bit weird because we have more subarrays of length m, so it might seem like one of them has to be smaller, right? But that's not always the case. And actually, there is a sample to this problem because we need to have samples, of course. So this kind of gives away part of the paradox, right? We need to have a sample. So you can just look at the sample, see what is actually going on there. And if you do that, you might notice that there are big numbers in the middle. And if you have big numbers in the middle, as long as m is bigger than half of n, the number in the middle will contribute to every window of size m. But it's going to be a larger portion of that window than to the whole window. Like it's going to have more of an effect on the average on these smaller windows than on the whole array. And if you do the math, you'll find that the total average, in this case, we only use ones and put a 2 in the middle. The total average is 1 plus 1 over n, whereas the average of each of these subarrays is 1 plus 1 over m, and this is a bigger number. So yeah, this construction always works when m is bigger than half. What about when m is smaller than or equal to n half? Yeah, that seems a bit trickier. Maybe it's just impossible. Let's just say that it's impossible and we submit this. I mean, why not? That might work, but it doesn't work. Okay, let's see. Can we prove something though? Can we prove some case when it is definitely impossible? And it is impossible when m divides n, because then you can just split up the whole array into blocks of size m. And the average of all of the numbers will be the average of the averages in these blocks of size m. But then all of them can't be bigger than the total average. Like if you take the average of some numbers that are all bigger than something, then that average will be bigger. So you get a contradiction here. So if m divides n, it's not possible. Like if m is equal to n half, for example. But if m doesn't divide n, but is smaller than n half, then we haven't solved the problem yet. So maybe it is possible. Let's try and find a construction. So instead of using one big number, let's put multiple big numbers in. And our goal is to try and make it so that each subarray of length m gets one of those big numbers. And it turns out that we can just put them like this. We put the big numbers spaced m apart. And you try to make it so that there are as few big numbers as possible in the whole array. And you can do that by putting them as late as possible. And yeah, if you do the math now, you'll find that since like the average of the subarray is again 1 plus 1 over m, but since m doesn't divide n, you get like this floor thing, since there are fewer than 1 divided by m big numbers in the whole list, and you actually get something smaller. And okay, I can also comment that one way to find this kind of construction, in this problem, you can do a lot with just brute force experimentation. You can write a brute force that generates random arrays and just check for numbers like 5, 2, 7, 2, 7, 3, and see what it finds and try to see when it's not possible. Like here you can really do a lot of work without thinking this problem by writing brute forces and checking for patterns. That's something I would recommend, or you can figure this out. Okay, so in summary, yeah, if and modulo m is 0, then it's impossible. Otherwise, you can do this. Okay, but in real life, how can this happen in real life? Actually, the inspiration for the problem is that it happened to me when I ran 15 kilometers.
You can sort these pairs with respect to their C value. Okay? And if at some point you can't, like, so start with the smallest one, and if at some point you can't afford it, then you can't afford anything above it, and you're done. Okay, so the solution is basically sort the pairs with respect to C, respect to C, and yeah, and then then go through them and buy them if you make more money. So buy if you have enough money and you make profit. And yeah. And there were interesting solutions that, for example, one interesting was I saw some solutions that had that, like, when they couldn't buy more, they did an else and just did a print, which works well, except that if you can buy everything, then you forgot to print at the end. Yeah, so that's the kind of fall that traps if you have this problem. But I think most people did the AC on the first one or on the first attempt. But yeah. Okay, so let's go to the next one. Which one is that?
With the permutation windows. Okay. Yes. So the next problem is permutation windows. And the problem is that you're given an array of numbers, integers. So let's say 1, 3, 4, 2, 5. And then maybe like more numbers here. 1, 2, 3, 4. Okay, nice. And you want to answer for all integers k between 1 and n, the number of integers. Is there an interval of size k such that the k integers inside here form a permutation of the numbers 1 to k? So for example, in this case, we have this interval that creates a permutation of 1 to 5 of size 5. And then we also have the permutation 1 to 3 here, for example, 1 to 4 here, and so on. So we want to answer this for all k's and print out all the k's such that there exists such an interval. Exactly. So we can start with the subtask, which was when the number of elements was fewer. One solution is to just look at all possible intervals and check if they form a permutation. So we have then of n squared different intervals that we can look through. And for each interval, we will do O of n work by checking if all the numbers are exactly 1 to k. We can put, for example, everything in a set and then check if they form 1 to k. And that would solve n less than 100. To solve the next subtask, which was when n was less than 1000, meaning that we want to have some kind of quadratic solution, we want to somehow make this more efficient. And one way to do that is that we can, for each k, do some sliding window solution. So then we fix the k, and then we want to check for all size k intervals, check if they form a permutation. And one way to do that is we keep this, we can keep track of, let's start with a size k. In this case, we can set k equals 4, and put all the elements here into some data structure. And now we want to just verify fast if this is permutation of the numbers 1 to k. One can do this with probably a segment tree, but an easy way to actually formalize what we actually want is to think about what does it mean to be a permutation. And we can write down basically three egenskaper, three properties, which is basically that for a interval of numbers to be a permutation, we need all integers to be unique. We need the minimum to be 1 and the largest to be k. We actually don't need this one, because if the numbers are given to be between 1 and n and the largest is k and they're all unique, we have a permutation already there. So then what we can do is we need to, for some way, check that for when we have an interval of numbers, check that the largest number is k, and check that they are all unique. And one way to do this is, for example, to have a heap, a max heap, a max priority queue, to keep track of what is the largest number, and to check that they're all unique. We can also have some data structure that counts how many of each number we have in this interval, and then do some query over, for example, a segment tree. That could be used. Yeah, that's one way to do it. Another way is to, for example, check for each integer what is the closest next index that has the same number. We do some pre-computation to calculate that, and we can do some minimum or minimum query over that. There are different ways to do this, but and all of them can make us can less easily solve what a quadratic solution for this. And to make this even faster, to be able to solve for bigger n, meaning that n less than 1e5, I think it was 3e5, we had to do something more clever. So let me just remove maybe some of these things. Yes. So now we somehow want to check and find the interesting intervals that form these permutations. And one way to do that is to just assume that we want to fix and iterate over something. So one thing we can iterate through is what is the largest number in this interval. What we can do is when we have this array, we iterate through each element. Let's say now we have iterated and we are on this element. We assume that this is the largest element in the interval that we're interested in, which means that if we fix this as the largest element, we can, what is interesting then is to only look at all the elements to the right until some number that is larger or equal to it. So we get some kind of like sub-interval where all the elements are, except this one, is less than 5. And now we have this sub-question, which is there an interval containing this of size 5? Because we have fixed the largest element. So it has to be of size 5. That is a permutation. And already there, to find this interval, we need to do some pre-computation, but we can come back to there. And now, basically, for a fixed integer, we just want to find is there an interval that covers this index and is a permutation. And basically, what we want to find then is out of all these different intervals, check these two properties. And this property is already checked because we are fixing the largest element. So we just have to check if there's if any of these intervals have or contain only unique elements. And one way to do that is with the help of some pre-computation again. So if we pre-computed for every index and pre-compute how many elements can we walk to the right such that the interval starting from here contains only unique elements, that would help us a lot. So for example, here we would calculate, let's start from here actually. So for this element, how many steps can go to the right such that all the elements in this interval starting from here are all unique. So in this case, we can go 0 steps because there are no elements to the right. Here we can go 1 step because we can include this one. And here we can go 2 steps because because the answer for this one will be the minimum of the previous one plus 1 or the distance to the closest 2. So we can calculate this. For this one, it will be 3. This will be 4. And now we get to 2. And this one has already existed before. So the answer will be minimum of 4 plus 1 or the distance between 2 and the previous 2. So in this case, it will be 2. No, it can go 2 steps before. Yes. And we continue like this. This will be, we can either go 5 steps until before we meet another 4, or this one plus 1. The minimum is this one plus 1, and so on. This case will be 4. Okay. And now we have generated these numbers, which are kind of interesting. And now we want to, for this integer, for this index, find is there some interval that works. And basically what we want to check is out of these indices, is there a number that is more than k minus 1 or more? It's an integer here that's more than k minus 1 or more, because they kind of tell us how long can go until the integers become non-unique. And we can do this using RMQ, some range maximum query. We can do it with a sparse table or with a segment tree. But if we do it with a RMQ with some sparse table, we can answer these queries in over 1. And since we're doing this for each index, it will be O of n for answering queries, but constructing the sparse table would be n log n. Or we can use some really nice ways to make it linear time as well, but we can ignore that. So the solution would run then in n log n computation and O of n to answer all the queries for each in this.
Also, an actual thing to note, nothing to be noticed, you don't even count the number of feasible something, but it's a number of fours. Or number of, yeah.
Yes,
You could even analyze a couple of even more.
that's true.
But that would be
Yes, but yeah, that's the solution for permutation windows. And which is the next problem?
plague,
Plague. Yes.
horrible plague. So this is the 200-bit plague. So the way this works is that in this problem, you are given n bit strings. Of length 200. Okay, and the way this works is like this. So this is thought to be a DNA of some kind of a virus that I think was happened centuries ago. But anyway, so this is some kind of virus. This is the DNA of that virus, and the way it works was this. So the DNA started out with a virus with some bit string. Okay, then every time it mutated, randomly 25 of these bits were chosen and flipped. Okay, so maybe it started out with all zeros, right? And then after mutation, what happens is 25 of these were flipped. I'm just going to write some of them here as being flipped, right? And then there was a mutation more. Another mutation, maybe this one got flipped, maybe this one got flipped back, right? And then, but otherwise, it's quite similar. Okay, so you have all this, and now what happens is that the data you've been given is this, but scrambled. And now your task is to try to figure out, like, what was the chronology? Yeah, what was the original order of these bit strings? And with the eye, you can actually tell relatively easily which way to go because you can see which two are similar, and then you like think, well, this one must come next to this one, and then you can continue doing that, right? So with the eye, you can kind of tell how to do it. And also, and something to note, by the way, because there's so many bits here, 200 bits, and 25 of them get flipped, what will happen is that you will never have the case where, like, if two look similar, they really are next to each other in this chain. So, like, it couldn't be that this guy and this guy happens to have also 25 bits away from each other. So you really get this nice looking chain. The question is, how do you find it? Okay, and in the quadratic subtask, when n is 1,000, then you can easily find it by just what you do is just you pick any arbitrary bit string, and then you try to find these two neighbors, or possibly is one neighbor if it is the starting one, and then you just keep making this like you pick a guy, and then you somehow build this chain upwards and downwards, and then you found the order. So that's how to do the quadratic one. The full task, however, is much more complicated because when n is like 2 times 10 to the 5, what happens is that you obviously can't do a quadratic algorithm anymore, and but you want to do something, and the way the solution works is like this. Take let's say at random 15 of these bits. Okay, so mark down 15 of these bits. Maybe this guy, maybe this guy. Do 15 of them roughly. Like you can choose a little bit more you want, but let's go with 15. Okay, so pick 15 of these bits and only look at these bits. Okay, note now that it's rather likely that two of these that are next to each other will be equal on all of these bits, all of these 15 bits, right? It's not guaranteed at all, but with a relatively high probability, definitely not zero, like the two neighbors will have the exact same values on all of these 15 positions. At the same time, it's also quite uncommon if you take two bit strings that are far away from each other in notation, that they would have the same value in all these 15 positions, right? Because essentially what these things are doing is scrambling the bits. So you will get roughly n over 2 to the 15 number of bit must have a specific value. So now what you can do is you can do this kind of buckets where you put everyone at the same value in the same bucket, and then you run the quadratic algorithm on that. Okay, and then you get some of these chains. You don't get all of them, because if you are unlucky and there was a bit of flip in your mask that you picked, right? Then what you have to do is basically you have to run this again, pick another 15 bits randomly, look at the new buckets, and then try to figure out the quadratic algorithm. And also another thing to notice that if you're a little bit smart about how you implement it, once a node has found its two neighbors, then it's done. So what will actually happen is that after the first iteration, the first couple of iterations, you will start being able to just completely remove the nodes when you're working. So actually, the program runs instant after a little bit, right? So the first iterations, you might have a lot of work to do with this kind of quadratic matching algorithm in the buckets, but the amount of things in the buckets will actually become smaller and smaller. Yeah. So yes, but anyway, so this is the intended solution. Yeah, and I think this is a nice problem. I'm also quite sure that there's probably a lot of different ways you could try to solve this problem in other ways. I think it's quite an interesting one from the different approaches. For example, you could try to maybe look at all the ones that have a 0 at the start and versus all the ones that have 1 at the start and do something based on that. So I'm really interested if someone can come up with another way of solving this than these buckets. But yeah, okay. So let's. I don't know which one is the next problem after this. How do you?
Yeah, I'm gonna check this. Yes. The KTH conjunction.
Okay, the junction problem.
Yeah.
Okay, so the K. You probably realize why I put this name. There might be some. I tried putting things into like a random, like a Wordle guesser thing, and it said K threshold, and then I had to use that. But anyways, so in this problem, you're given a directed graph. Okay, just your typical directed graph. It has nodes, it has edges. It's guaranteed that there are no multi-edges, no loops. You're also given a number K. And you are given, on top of this, you're also given a list of T cycles. Yeah, so given T cycles, and these are simple cycles in the graph. And the question is, does this list contain all simple cycles of length smaller or equal to K? So that's the question. Does the yes. Okay, so this is a rather difficult question. Okay, so let's first just deal with the subtask. So subtask was T is guaranteed to be 0. So basically, the list is empty. So the question is essentially, when T is 0, you haven't given any cycles. The question is really just, does there exist a cycle, a simple cycle in the graph with length smaller than or equal to K, right? How do you solve that? Well, there's a very easy algorithm to doing this. Just try every node, do a BFS, and see can you get back to the starting point in less than K steps, less than or equal to K steps. In that case, the answer is there was a cycle, and this list that was empty is incomplete. And if you can't get back to the starting point, there wasn't a cycle, and the list is complete. Okay, so basically what I'm trying to say is that subtask T equals 0 is just BFS from every node. Try from every node. BFS from every node. Okay. So in the general case, then it becomes a lot more trickier, right? Because now somehow we have this list of cycles. One question you might think, can we use it? And my intended solution do not use this at all, by the way. So I'm not even looking at this list. All I'm doing is counting if the T number is correct or not. So how do we find cycles in a graph? Well, so the way you if you want to just have an algorithm that finds all cycles in a graph, the easiest way to do it is to just do a DFS, start at any node in the DFS, and just try every possible path. Okay. The problem with doing this is that it might be that the graph has a lot of different paths that are not cycles, so this would run in exponential time. So we have to do something smarter. And what we can do is this. We can do a DFS, the same kind of idea, but that is guided by a BFS. So the idea is that when you do a DFS, you kind of like you want to close the circuit, right? So what you do is you do a BFS from the endpoint you want to end up with, and you do it backwards, and then you check: is there a way if I expand in this direction that I come back in the so I get less than k steps in the end? So you do this kind of DFS guided by a BFS, and that way, whenever you do any kind of work in the DFS, so every iteration of the DFS, you do this kind of BFS. You know that you're always making progress because you're always getting closer to finding a cycle. So you're always getting closer to finding anything on this list. So by doing these two together, by doing a DFS that's guided by a BFS, you're somehow always making progress. And if at any point you were to find a cycle that's not on the list, then you're done. Or if the list became too long, you're basically you're done at that point. Because then the thing must be incomplete because you found too many cycles. And that's one plot twist more about how we solve this. So a problem with cycles is that if you have a long cycle, then you will find it multiple times with this approach because any starting point with the DFS will find the. So if the cycle is like n long, you would have to find it n times. And the way to only find it once is that when you're looking at a certain node as a starting point, then what you do is you remove everything in the graph, all the nodes that have an index that's bigger than that node. So just remove them from the graph. Look at the subgraph where you have everything is small or equal to that node index. That way, you will only find a cycle when you're looking from the node with the highest index in that cycle. So that way, instead of finding like 1,000 known cycles 1,000 times, you only find it once. So it's DFS guided by BFS together with this kind of subgraph. These two together is what is the solution. And as for time complexity, the time complexity is just you're doing every time for every value in this list you're doing a BFS. So it's essentially the size of all of these times the size of the graph. Okay, I found this a little bit interesting, but the thing that to really remember if you didn't solve the subtask, it's a quite easy thing. Just BFS starting from a node and C, is there a path that you get back with length small equal to k, and then you found the cycle. So the subtask was a lot easier, I think, than the full problem. Okay, what is it?
Yes.
Nice. So which one is next?
Next one is bucket list.
Okay.
So we're going back to Nils.
Okay, so the last problem here is bucket list. This presentation of this will be a bit shorter because I couldn't be bothered to make proper slides, but hopefully it's good enough. In this problem, you are given tasks on a bucket list. Each of the tasks has two limits on how old you can be and how much money you need to have. But after completing the task, you become older and poorer. And that makes it harder to complete the other tasks. And now we need to find a way to order the tasks so that you can complete all of them. Okay, so here it might seem like it's a good idea to sort the tasks with respect to something and then try to complete them in that order. And in many of these kinds of problems, that is a good idea. So this seems like a scheduling problem. Like the limits we have are kind of like deadlines, and the penalties we get are that's like the duration. And actually, subtask 1, when we only have one resource, that reduces to just a classic scheduling problem. And you can sort if you sort all the tasks with respect to, I forgot what it was, but I think, yeah, beta minus b, it turns out to work. But in the general case, this doesn't really work. Okay, so instead of that, let's try and think about a different problem. So in our problem, the tasks become harder and harder because your resources run out. But what about if they became easier and easier? If you gained resources? And this is a very common type of problem. Like, they are usually framed like you have a video game and you need to defeat monsters, and each monster you defeat gives you some XP and money or whatever, and then you get more resources, and that allows you to defeat more monsters. And actually, in this contest, you have the shop randomizer problem, which is exactly this kind, but with just one resource. And in those kinds of problems, it's always optimal to just always pick any task that can be reached and just completing it. It doesn't matter which one you pick, because after completing it, it becomes easier to complete more tasks. So it's never a bad idea to pick one of them. So you just need to find a way to update like which ones are reachable and how do we grab one of them. And so you need some data structure, but in the whole idea is just grab any that's reachable. But our problem is the other way around. It doesn't become easier, it becomes strictly harder. So what should we do then? We should do the opposite, right? But what is the opposite? So let's simulate the process in reverse. So we need to complete all of the tasks. We don't need to maximize how many we complete. It's all or nothing. So we know that in the end, we have completed all of them. And from there, we can consider what is the last one we completed. And then we undo it. And then we keep going like that. And when we undo tasks, instead of getting older and poorer, since we are doing it in reverse, we actually get younger and richer every time. So it becomes easier to undo more tasks. So if you just do it in reverse, you literally get this other version when things get easier and easier instead. So now you just need to solve that. And now this is a bit of a data structure problem. You have like 2 dimensions and you need to pick. You need to be able to keep track of what is your money and age right now and which tasks can you pick. I'm sure you can use some 2D data structures to do this, but the easiest way is to sort with respect to one of the resources. And then you just need to be able to take the best one with respect to the other resource. And you can just have a priority queue to do this. So yeah, that's the problem bucket list. I think, yeah, going in reverse is really the main idea here. And that was it. That was all of my tasks. Hope you had fun in the contest. Hope you liked the other problems as well. The Minesweeper one is pretty fun. I like that one. Yeah, goodbye.
Okay. Thank you, Niels. Yeah, let's do Minesweeper.
So in Minesweeper, or in Minekeeper, this happens to be similar. No. The idea is that, yeah, okay, thank you. Yes. Okay, yes. And what was the number? 2411. Yeah, 2411. So the idea is like this, right? Suppose you take a complete finished board of Minesweeper, and then suppose you remove, like you mark a question mark on all spaces that have a mine and all spaces that are blank. Okay. The question now is, can you figure out like which ones were mines and which ones were black? So here's an example of a board where I removed all of the possible, all the blank and all of the mines. So you can see this one was either a mine or blank. This was either a mine or blank. This was either a mine or, yeah. And the question is, can you reverse this? Can you somehow figure out which ones were mines, which ones were blanks? And also something to note, by the way, there are situations where there could be multiple solutions. And because I just wanted something a little bit simpler to check, instead of asking you, can you reverse this? I ask you, mark down every space that could have a mine in some solution. Okay? So now the question is, what should we do here? So like the numbers are the same, it's just we have to figure out what the question mark should be. Like where are the mines and where are the blanks? And for so the first thing to note is that if you have two squares like this that are connected, like this or like this, like diagonally or next to each other, then they must either both be mines or both be blanks. Right? Because the rule of Minesweeper is that if you have a mine next to a square that's not a mine, then it has to be a number. So connected components must be the same thing. That's first thing. Okay. So that means that either all of these will be like mines or yeah, these have to be the same and this one has to be the same. And now we can try to figure things out here. Let's see. So we need, because this is a 1 and this is the only question mark next to it, we need this to be a mine, right? So now we know that there is a mine. Yeah, I will probably go M here. We know that it's a mine here, and then because of connected component, every one of these are mines. And now the question is, are we done, right? Like, are all of these, yeah, this is satisfied, this is satisfied, all of them satisfied. So clearly this must be a black. Okay, so this is the solution to this board. And this one didn't have double 2 solutions. But I can easily write another board that has 2 solutions by having this kind of evil. Let's see. So I have like a 1, 2, 2, 2, 1 kind of thing. Right? Here the problem is we know that all of these are, so if all of these are question marks, right? Then what will happen is that there are clearly 2 solutions here, right? There is, so all of the ones on the left must be the same, and the ones on the right must be the same, but the 2 solutions, either all of the ones on the left are mines and all the ones on the right are blank, or the other way around. Right. So the solution for this board would be just a lot of mines, basically. So yeah. 1, 2, 1. 1, 2, yeah. And then M's here again. Okay. So this is how the problem was, and how you kind of think of it. So now the question is, what do you do? And the way I like to think about this is, suppose it was just what? Okay, suppose this was just a one-dimensional game. Okay, so suppose you had this kind of thing where you had like a question mark, maybe a 1, maybe another 1, maybe a question mark. Yeah, suppose you had this kind of one-dimensional grid here. How do you solve this? Well, suppose you knew what was in this. Suppose I revealed to you what was in the first square here on the grid. In that case, you always know what the answer is, right? You can actually then solve this guy, but depending on what is left to left of it, right? Because if this is a question mark, if this was a mine, then this also has to be a mine. If this was a blank, then this also has to be a blank. If this was a number, then you can simply see this is to be a mine or not. So the trick is in the 1D case, you can like use, you have one choice possibly. So you have you have one choice here. Is this blank or mine? But after that, you get a unique solution by just looking to the left. So this proves that on a 1D board, there are at most 2 solutions. At most. So it's smaller equal to 2 solutions. So what do you do if you have a bigger board, right? If it's not 1D, turns out you can do actually the same thing practically, but what you do is instead of going through the things from left to right, what you do is you do this kind of pattern like this. You go first this guy, then you do these 2, then you do these 3, then you do these 4. Like if you do diagonally out, then when you're looking like, is this guy, what is he? Is he, like, if there was a question mark here, you're trying to look, what is this guy? Then what you do is you look up left. And just like it is in the 1D case, where if you look left, you can tell what's going on, it's the same here. So if you look up left here, you can, from that, tell what is he going to be. So it's basically like the 1D case again. You have to somehow reveal the corner, because the corner you can never be certain of. But once the corner is revealed, then everything else follows. So again, you actually, just like in the 1D case, you can prove here that you also get at most 2 solutions. On this board too. Okay. So yeah, so start in a corner, go out like this diagonally, go through the squares, and then at each time point, you can figure out what's in the square by looking at the thing that's up to your left. Like if then you get to this nice solution, and you can see then that you have at most 2 solutions. Yeah, and I think that no solution passed on this problem that had this kind of messy thing. I was a little bit afraid that because it's kind of hard to make test cases, by the way, for this problem, because it turns out that these kind of properties having 2 solutions is quite uncommon. So I was really hoping that no one like did some kind of argument. Yeah. Is it possible to construct it as a linear? Yeah, I think it is. I mean, obviously this in some way, but yeah. I think that the pit you shouldn't fall into is trying to look at this like some big equation system, because that's when what these nodes could be and so on. Instead, it's much easier to just do a systematic thing. Go from the corner that you know things in, and then just go out from there, and then everything follows. So I think looking at the like, equation system is the wrong way to do it.
So my previous notes a bit. I don't understand how you can figure out the first row and the first column knowing only the corner.
Problems? Do we have any questions before we move on to the scoreboard reveal?
Can you hear me?
Okay, give me 1 minute because I have to bring it.
Yeah, that's the thing. That's the thing. Yeah. Okay. Det är liksom snabbt. Ja. Okej. What do you call can see? No. It's okay. So yeah, the answer.
We had a question, which is when we reveal the first corner, how do we know the rest of the column or first row?
So let's think about this, right? If this guy turns out to be a mine, right? Then we know by connecting components that because this is not a question mark and he's connected to him, we know that this is a mine too, right? And now what we should do if you follow my he's connected to a mine, so he's also a mine. Now, now we're here, and yeah, this one is already known. It's a 1. We can continue. This one we're trying to figure out now. Yeah, he's connected to a mine, so he's a mine. Again, this guy is connected to a mine. He's a mine. And now what happens is we get here, right? And the interesting thing is that now when you look at this guy, free. Yes. Okay. It makes much more sense now. Okay. No, it was to be 1. No, 2 is correct because then both of these are mines.
Last question.
Yeah. But anyways, so now when we get to this guy, what happens is we already know that these 2 are mines, which means that this. Then you have to be black. And then we just continue like this. 3 is it's known already. And then you have a question mark here, it's an extra mine. Yeah. So you can you have to think about it a little bit. And it has a lot to do with this kind of thing where if you're connected to a mind, then you're a mind. If you're connected to a blank, then you're blank. And if you're not connected to a mind or blank, then everything around you, everything.
Nice.
Yes.
Okay, let's go on with the solution presentation.
Yeah. Or with a reveal.
Yes, solution reveal. Yes. Okay. So we haven't set up a. We have this up, which is the cool scope reveal. We're gonna scroll up. We're first gonna look at the general scoreboard, and then we're gonna look at the on-site scoreboard to present the prizes to the winners on site. Okay, well, let's go. So let's have some crowd participation. Yes. Okay. I'm gonna scroll up, or let's do. Yeah. Let's just. We see that most of the people are trying to solve the problems B, C, H. We can slowly move upwards. And here we start to see that we have some solutions for F as well. Some people are getting subtasks on I, G, and A. And yeah, what else looks like. And now we get. Okay, and now we have top 15. Exactly. Whoa. Okay, and now we get to the top 10, and maybe we can present the names here. So on the place 10 of KTH Challenge 2026, we have. Let me unmute. Hold on. So we hear more crowd. Oh, okay, let's go. And on place 9, we have. And on place 8, we have. Oh, yes! And on place 7, we have. Oh, Arvid Jonasson! And 6, we have. Oh, Alexander Kraberg! And on place 5, we have. Oh, Andreas Björklund! And on 4th place, we got. Oh, Simon Persson Holm! Okay, and now we're getting to top 3. So on 3rd place of KTH Challenge 2026, we have. Oh, Loke! On Joshua! And on 1st place, the winner of KTH Challenge 2026 is. Oh, Erik Adebar! Huge congratulations to everyone.